Okay, hello. So this is problem 8. Find the two-dimensional volumes, or the two volumes, of each of the triangles with vertices listed below. And there's 3 parts to the problem. So these vertices are in R2, and so the triangle just looks like something, and the 3 vertices give the triangle. The triangle is the convex hull of these 3 vertices. We'll learn that in a little bit. And this would be sort of in the plane. I don't know, maybe it's the xy plane. Doesn't really matter. And then we can go to space and find our 3 vertices. Maybe here is A, maybe B is over here, and C is there. And still, these 3 vertices define a triangle, and now here it's sitting inside of 3-dimensional space, but it's a 2-dimensional object, so we'll find its 2 volume, which is also known as its area, or its surface area. 2 volume equals area, because we'll also want to find, there's 3-dimensional volumes, there's 1-dimensional volumes, which are lengths, there's 4-dimensional volumes, 5-dimensional volumes, etc. Okay, and then in 4 dimensions we can't draw it, but somehow 1, 2, 3, and somehow like a 4th dimension, there's 3 points somewhere, and their convex hull is again a 2-dimensional object. Even though it sits inside of R4, it's still 2-dimensional, and we can find its 2-dimensional area. Okay, and well, how do we do that? So in every single case, the formula is the same, and we will use this formula in integration later, so it's an important formula. The square root of the determinant of the Gram matrix. And so what is the Gram matrix? So first, for each triangle, we'll sort of pick 2 vectors that are spanning it. And it doesn't matter which ones we pick. We just have to get 2 vectors. Because the Gram matrix of these 2 vectors, let's call them V1 and V2. The Gram matrix, like I could say the Gram matrix of V1, V2 is equal to, well, take the dot product of V1 with itself, and then the dot product of V1 with V2, and then the dot product of V2 with V, basically all possible dot products. V2 with V2 is the last one. And actually, this one and this one are the same, and we put them into a matrix. It'll be an array of these 4 numbers. And it'll be a symmetric matrix, which just means that this and this are going to be the same number. Okay? And so let's just compute this. So for this triangle, let's choose V1 to be, let's say U minus is V, and then V2 to be U minus W. Or, well, here, so U, V, W. So then I guess to match the drawing, it'll be W minus V. And so what's V1? V1 is U minus U minus V. So I look up here and I take U minus V. So 2 minus 1 is 1, and U minus V will be, final minus initial, 3 minus negative 1. 3 minus a negative 1 is going to be 3 plus 1, so that's 4. Okay, great. V2 is W minus V from my picture. It didn't matter what I chose, but W minus V will be 4 minus 1 and 0 minus minus 1. So that'll be 3. 4 minus 1 is 3. 0 minus minus 1 is 1. Okay, so then I just compute these dot products. The dot product of V1 with itself will be 1 squared plus 4 squared. And that's a what is that? 16, 17, okay. The dot product of v2 with itself will be 3 squared plus 1 squared. So that's 9 plus 1 is 10. Okay, now the dot product of v1 with v2 is going to be 1 times 3 plus 4 times 1. 1 times 3 plus 4 times 1, that's 12. And it's symmetric, so we already know that that's a 12. So here's our matrix of 1, 2, 3, 4 numbers. And so what do we do? So now, remember our formula is the square root of the determinant of the Gram matrix. And so what's the determinant of this matrix? So if we have a matrix A, B, C, D, its determinant is AD minus BC. And so the determinant here is 17 times 10 minus 12 times 12. Okay, 170 minus 144. Okay, 4 needs 6 up to 50. 50 needs 20 up to 70. So 6 and 20, 26. Okay, so that is the determinant of the Gram matrix. And so I just take the square root. And so because we actually can't calculate square root very well, as a human, we have to ask a computer to approximate it. But we can just write a squiggly line. And so usually we just write the squiggly line. But we could have also written SQRT of 26. And these are the same. We're just basically giving up and not computing the square root of 26. I mean, we could roughly, okay, so like 4 squared is 16, 5 squared is 25. Okay, so it's probably like 5 point something. I don't know, 5.1? I don't know. So we could sort of roughly get it, but let's just write square root of 26. Is that it? Okay, so these 3 points in the plane give a triangle, which is, oh, there's one more thing here. So this formula, square root of the determinant of the Gram matrix, gives, see how easy it is to make a mistake? I just made a mistake. This formula, well, I'll put it in pink now. It gives the area of the parallelogram spanned by these two vectors. In every case, so here's the parallelogram there, there's the parallelogram here. And so what I have to do is take 1/2. So actually 1/2. And so that's my answer for this triangle. This is the area of the triangle. Okay. So this same process, we'll just have to repeat it now for these other triangles. So let me just copy it. Copy. Let's move over here. And let's see if we can, so right away we know that we have these 3 points. 1, 2, 3. They're somewhere. They happen to be in R3. So they're in space. But we really want 2 vectors because those 2 vectors will span a parallelogram and we'll take half of the volume of that parallelogram or the area. And so, I don't know, we just need to subtract maybe this minus this, this minus this. It doesn't really matter, just so long as we sort of choose a base point and then do the others minus it. So like if, let's see, like if this is A and this is B and this is C, then in my drawing I chose C as the base point. So I would do A minus C and B minus C, final minus initial. Always tell that. This is what I always think to myself, final minus initial, in order, gives a vector between 2 points. Okay. So why don't we do that? So A minus C, 1 minus 6 is minus 5, minus 3 minus negative 2 is minus 1, minus 2 minus negative 5 is 3. So this is our first vector, v1. here my v1 was a minus c. Okay, so then my second vector, how about b minus c? 2 minus 1 is 1. 0 minus minus 3. Negative 4 minus minus 2 is minus 2. Okay, so now I have my two vectors. Now I take their dot products. So I take, remember I want, well, I guess 1/2 the square root of the determinant of the Gram matrix. Okay, so what's the Gram matrix? I need the dot product of v1 with v1. So that's going to be 25 plus 1 plus 9. The dot product of v2 with v2 is going to be 1 plus 9 plus 4. I'm summing the squares of each of its components. But now I need to actually, because that was the dot product of a vector with itself, but now I want to take the dot product of v1 with v2. So now I'm not summing the squares, but I'm summing the products among each component. So I'm going to get a minus 5. I'm summing, so I plus. Minus 3. And a minus 6. Okay, so lots of minuses. I'll collect them. 9, 14, minus 14. Pluses, this is 14, and this is 35. Okay, and it's symmetric, so I could do the dot product of v2 with v1, but I already did that. So here's the Gram matrix. Now I take its determinant. That's this times this minus this times this. Okay, 35 times 14 minus negative 14 times negative 14, which I'll just write as 14 squared. Okay. Great. I really don't want to compute that number, so I'll just leave it like that. This is the determinant so far. And now I take 1/2 the square root of this number. And that's my answer. So that, just to make sure I understand what I just did, the area of triangle in R3 equals 1/2 times the square root of some number. And that number is the determinant of this Gram matrix, which we will use when we do integration. Okay. Great. One more problem to do. It's this one. Oh, this one looks, I automatically can see it's going to be easier because there's lots of zeros everywhere. When I go over here. Okay, lots of zeros. So, ooh, bless you, my new. Okay, so let's do, so I just need to subtract them to get two vectors, right? Because what I have here is 3 points in R4. But I subtract them to get two vectors, so what are my vectors? How about 3 minus 1, 0, 0. So I did this one minus this one. Well, okay, I did this one minus this one. Okay, and then V2, we'll do this one minus this one. Because remember, okay, so I want to do, here, let's label what I'm going to do. A, it's always good to go to your picture. I want to do, then I guess, like this. Because what I've drawn is A minus C, B minus C. Those are my two vectors. In other words, we need like sort of a base point for our vectors. And I want to make sure I'm doing the subtraction correctly. So now B minus C gives me this vector. So 0 minus 0, 0 minus 1, 1 minus 0, and 1 minus 0. Okay, so 1/2 square root determinant of the Gram matrix. Okay, so what's the Gram matrix? I have to do a bunch of dot products, right? So dot products give you lengths, or actually length squared. So it makes sense that from the dot product we can somehow extract the volume. And this formula will work in every single situation, which is why we're going to use it in this class. So v1.v1, and remember, people write v1.v1. Sometimes they write in brackets v1 comma v1. Sometimes they'll write, I like to write like this, v1, like a function, dot, and it takes 2 arguments. But regardless of what symbols you use, it'll be a sum of squares in this case, 9 plus 1 plus 0 plus 0. v2 dot v2, I like to do those ones first. That's negative 1 squared is going to be 1 plus 1 plus 1. And then there was a 0 there that I didn't write. And v1 dot v2 is now going to be sum of products. So 3 times 0 is 0, plus negative 1 times negative 1 is 1, plus 0 times 1 is 0, plus 0 times 1 is 0. And so this gives 1, this gives 3, this gives 10, and it's symmetric, so there's another 1. Okay, so what's the determinant of this 2 by 2 matrix? It's 10 times 3 minus 1 times 1. Which, okay, I guess I can do this. 30 minus 1 is 29. Okay, so the answer is 1/2 of the square root of 29. And that's the answer. And what is this number? It's the 2-dimensional volume equals area of triangle in 4-dimensional space. Okay, so that's good. We're going to need this because later, when we're integrating over surfaces, like let's say we have some surface here, and it's some curvy surface in space, or higher dimensions, or wherever it is, and we want to integrate over it. Later, we're going to see that at every point, there's going to be a little parallelogram attached. And at every single point, this parallelogram will have different sizes. And we'll be able to count, from the derivative will give us these 2 little arrows. And what goes into our integral will be the square root of the determinant of the Gram matrix of those 2 vectors, which come from the derivative. And so this will be some number that we need to stick into our integral in order to get the correct answers. And I really think this is a great formula because it works in any dimension. It works for curves, it works for surfaces, it works for 3-dimensional objects, 4-dimensional. It works for polar coordinates, spherical coordinates, cylindrical coordinates. And so we're seeing it already here. And it's basically just coming from these dot products. Take dot products of vectors, and then for areas of triangles, they'll have these 2-dimensional volumes, and so we'll have a 2 by 2 matrix. And later, when we're integrating over surfaces, we have 2 vectors, and again, we'll have a 2 by 2 matrix. This will be the Gram matrix. It's a matrix of dot products. Okay, that's it. Okay, that was problem 8.